Hello everybody, welcome to the presentation on our work Improved Soft-Aided Decoding of Product Codes with Adaptive Performance Complexity Trade-off. This has been presented at this year's European Conference on Optical Communication. I'm Susie Miao. This is a joint work with Luca Papp and Laurent Schmalen. I will briefly motivate this work. We look at product codes, which is a kind of powerful code construction very suited for high-speed optical communication systems. And conventionally, we have two ways of decoding product codes. One way is the soft decision decoding, SDD, and the other is the hard decision decoding, HDD. And SDD with the most famous example as the turbo product decoding, the TPD algorithm achieves a very good decoding performance, but also it has very high complexity, and especially the internal decoder data flow is very high due to the passing of soft messages. And on the other hand side, we have HDD, or mostly just refer to the iterative bond distance decoding IBDD, which has a much lower complexity and it only passes hard messages, but the decoding performance is much worse than the soft decision decoding. So what we are trying to do here is to look at something called soft-aided HDD. So we try to keep the low complexity and low internal decoder data flow as in the IBDD, but we try to approach the SDD performance. So to do this, we first need some preliminary on the iterative decoding of product codes. So here you can see, let's focus on the left-hand side. This is a block of product code words, and every row and column is protected by a component code. Typically, we use the BCH or Reed-Solomon code. And during the decoding, we first decode all the rows with the component code decoder DC. Then we pass the updated value to the column decoders. Then all the columns are decoded, then the messages are passed back. So this is the iterative process. And the difference between SDD and HDD is one thing. The DC could either be a soft decision-based decoder, for example, the Chase2 decoder, or a bonded distance decoder for the hard decision decoding. And the message passed in between could either be soft or hard. Okay, so we try to improve the IBDD. So what we do is we first need to see what makes IBDD worse than the TBD. We can summarize the reason. The first reason is the high miscorrection rate and the error propagation caused by the miscorrections. So what is a miscorrection? Miscorrection means that if we have a vector y, then we decode it with DC, then we successfully found the code word, but it is not actually the code word that was transmitted. This is not, it's generally not very common, but it especially happens very often for the ECH and RS code we use in optical communication systems, because here we use high rate codes with small minimum distance, and some research shows that they are most prone to the miscorrections. So this is the first factor. And second one is that if we use DC as CDD, it can only correct a very small number of correctable errors. So here is the example. We look at the exemplary product code, and here on left-hand side we have the TBD, and the right-hand side we have IBDD. And we can see that even if we have an ideal case where we discard all the miscorrections made by the IBDD decoder, then we can see that it gives us some improvement, but the gap to the TBD is still very big. So we can say that if we don't increase the correctable errors by the bonded distance decoder it is very hard to achieve a better performance. So we can now give our solution. The one thing to deal with miscorrections, we introduce dynamic reliability score, we call DRS. And the second thing is we enhance DC to a list-based decoder, which decodes a bigger number of errors. And very interesting is that the bigger number of error we can correct, we are actually more prone to miscorrection. So it's also very important to find trade-off between these two, but this is what we do. So first thing, we look at DRS. So we consider the simple BPSK signal transmitted over binary input AWGN channels, which means that the reliability of the bits is proportional to the absolute value of the received bits. So based on this, we can initialize the DRS. So the DRS are integer values represented with 5-bit integers here for easier implementation. And we initialize it based on the absolute value of the received bits. So what we do is we sort and divide the channel outputs into even groups. So the bits with high magnitude will be assigned to a high DRS, will be assigned a high DRS, and the bits with small output value is going to have a low DRS. So this is the initialization, and then we can introduce the mechanism of updating the DRS. So this is very important because before us there were no way to update reliability of the bits for product codes without soft messages. So the only way we could do before was the TBD-like algorithm, which passed soft messages and do a complicated reliability update. But here we can update the DRS with hard messages. It is based on the observation that if we have a bit that the row and column decoders disagree upon it, it is very likely to be erroneous. So what we do is we increase the DRS by 1 if a bit stays constant during one iteration, and we decrease by 1 if it gets flipped during the decoding. And the values are clipped to 0 and 31, so it doesn't overflow. And we can use it to aid the hard decision decoder as depicted here. We have 2 criteria to detect miscorrections using the DRS. The first thing is the decision. We say a decision, if it's correct, it should not conflict with bits which is highly reliable or with high DRS. The similar ideas has been used in the previous work as well, and it's very effective. And the second thing is we found that we should limit the sum of the DRS of the flipped bits. So it should be small. It means that we shouldn't flip too many bits at the same time. So it's rather to be a bit more conservative during the decoding. Okay, and this is the DRS. And the second part, we want to enhance DC. So what we do is we introduce an error and erasure based decoder. So you can see here that usually we have a hard decision at the receiver, but here we introduce some additional erasures for the bits that has a small absolute value. So the idea is that it's because we have a BDD-based decoder. If we introduce too many errors at the beginning, then we cannot correct them no matter what we do. But if we turn some errors into erasures, there's still hope that we can correct all of them during the iterative decoding. So after this, we will fill the erasures with binary values, and the values are generated as pairs of complementary random values. And after this, we can start decoding with BDD. So here we fill them with J pairs, and J is the configurable parameters. So the bigger J is, the higher complexity it is, and also better performance. And we will show later how J changes the performance. And now we decode all the binary patterns with the BDD decoder, and then we perform miscorrection detection with DRS that we introduced earlier. Then we select the decoding results based on the Hamming distance of the decoded code words to the original received vector y. Okay, so this is the overall workflow of the algorithm, and the green part is the initialization. We have upper part, assign the DRS and store them in the register, and lower part we do a ternary decision and put them into the iterative decoder, and then the decoding is performed with miscorrection detection. Okay, now let's see how the algorithm works. So we first consider a product code with rate 0.87, and here is the performance of the TBD developed by Viasat. And the right-hand side, we have IBD, and we can see that the gap between them is very large. Then here are some previously introduced soft-aided algorithms. They close around half the gap, and this DRS-B plus is our previous work is already better, but there's still room for improvement. Now this is the newly proposed algorithm. We can see here are 4 curves. So basically, this is j equal to 1, j equal to 2, 3, 4, and 8. So basically, it tends to converge for bigger j. And so we can say that j equal to 4 is a rather good option for this code. And for this, we achieve more than 1 dB of gain compared with IBDD, and we only have a small gap to TBD. Okay, and we have another code with slightly lower rate and smaller size. And here we have a similar result, and the gap again is also very large, and we have only a small gap to TBD. Okay, that was all of my presentation. I concluded now. So in this work, we proposed a novel soft-aided HDD algorithm, which at the same time increase the number of correctable errors, but also avoid miscorrections. And it can provide a comparable decoding performance with soft decision decoding, but the complexity is only a fraction. Okay, thank you very much for your attention. And if you have any questions, you can comment below or contact us.